Mic's on. Hello and welcome to Lecture 2 of Introductory to Astronomy, Physics 1600 for people at Michigan Tech. An exciting and interesting and widely expanding, mind-expanding lecture today where we'll take you all over the universe and all the way down to proton sizes and subproton sizes in the realm of just a few minutes. But as usual, we start off with a what is this? So if you were to look at your screen, I guess I'm the bubble guy on the lower right, if I understand correctly. So I would be pointing to my right, I guess. What is this? Here you see a starscape with lots of stars, and there's two bright stars in the center. So you can ponder what that is. Well, go to the next slide. These are part of the two obligatory slides which we will have until people become nauseous every lecture. If people are just stumbling upon this on the web, it tells them where they stumbled upon and why they should go to another website or stay here. So this is Introductory to Astronomy. Today's lecture is Universe, Scale, and Light. So we will go over the scale of the universe and we will talk about light. The school where this is originating is Michigan Technological University, an accredited university in the Upper Peninsula of Michigan, which is really beautiful right now. And in the coming months will be even better with the fall colors coming out. I am your astronomy professor. I am Robert Nemiroff, at least most days. If you're taking this course for credit, then the only way to do that is to go to courses.mtu.edu. If you're just finding this online, don't go there. You won't be able to get past the login screen, and it will be frustrating. If you're in the class, you never have to come to class. But it's encouraged. If you do come to class, you can contribute questions that can be included in the weekly quizzes, in the midterm, and on the final. What you're responsible for. So what's going on? There's no textbook. This can't be right. Well, it is right. And here's what you need to do to pass the class. You need to be aware of the videos. You either need to come to class and watch me. I am the live video. I'm sort of like a video, but here I'm in person. You have to go to the Wikipedia entries that will be clearly labeled each lecture and read them. You won't be, turns out that this lecture, there's some Wikipedia parts that are high math. You're not responsible for anything having to do with calculus, integrals, things like that. You're responsible for basic math. You can usually tell from the quizzes what kind of content that I'm interested in. So I wouldn't go crazy on the higher math or worry about it too much. Every week there will be a quiz to make sure that people are following the course. So this week covers Lecture 2. Oops. Lectures 2 and 3. I should have changed that. Lectures 2 and 3. You're responsible for the astronomy pictures of the day posted during this week. So that would be from Thursday to Wednesday. But I will review them on Wednesday. So all you need to do is watch the lecture as well. But you should probably read the text of the APODs. The links in the APODs will tell you what the APODs say. So you're pretty much responsible for the paragraph there. But you're not responsible for the details of the links, other than that the links will tell you what the text says. So quiz 1 is due, I believe, today. I think it's 5 o'clock. Quiz 2 will be due next week at the same time. Will be released on Wednesday. And once again, this is where you need to go if you're interested in credit. So the Wikipedia pages covered today are Earth's atmosphere. Oh, I see people writing this down. They're taking this seriously. Light. Black body. Why that? This is sort of a why would be. We'll cover all these in class today. Something that sounds like Wien's law, but it's sort of German, so it's pronounced Wien's law. And the Stefan-Boltzmann law. Lots of laws today, but it's not that bad. You'll see. People are copying this down, so I need to stall for a minute. So the Earth's atmosphere people are generally familiar with because we breathe it a lot. Light, people are familiar with because it strikes people's eyes and stuff. Black body radiation we'll review. Everybody emits black body radiation. Don't try not doing it. Wien's law and Stefan-Boltzmann law have to do with the energy emitted by an object, even us. the energy, and the how many photons per second. So we will review all of that more than just these lines on a page. Okay, few people are writing. So if you missed it, go see the lecture or try someone near you. Okay, so we're going to do review of the universe now. This is kind of fun. So everybody put on your seatbelts here in class and at home. Hold on to your tables because we're going to be doing some going to some crazy places. And the first place we're going to do is we're going to go to a website you will see. I missed it, other one, called Molecular Expressions. I don't know if you can see this. So this content does not originate with me, and we are just showing the web here. So we're not stealing it, we're just showing the web. And this is micro.magnet.fsu.edu/primer/java/science-optics-u/powers-of-10. And they've taken the idea of the Powers of 10 video that were done by the Eaves brothers, which you can find on YouTube. And I think they've made it a little bit better. So I'm going to play it automatically. We're going to zoom in on our galaxy automatically. Every second it's going to take you, I think, another power of 10 closer, I think, through Florida and into a proton. And then I'm going to go out manually and describe things in more detail. So I'll just give a very cursory explanation on the way down, and on the way back I'll give more detail. So I'm going to click Auto, and we will zoom in. So here we're zooming in on a galaxy, something like our own galaxy. We're going to zoom in on a part of that galaxy. And there's lots and lots of stars. Stars look like clouds. Now we're going to zoom in on a star. And this star is our star. It's the sun. And then we're going to zoom in on our solar system. And zooming even further, we're going to zoom in on our Earth, because you know it because it has a blue orbit. Then that is the orbit of the moon. And then as we go inside the orbit of the moon, we see an Earth. And then as we zoom in on the Earth, we see a Florida. And as we zoom in on Florida, we see stuff. And now we're getting into trees and other stuff. Okay, now we're zooming in on the tops of trees. Here's a leaf in the trees. As we go, it's the magnification even greater. Zooming in on part of the leaf, zooming in on cells in the leaf. Individual leaf cells, the nucleus of a cell. Individual DNA strands inside the cell. Going further inside that, you see a carbon, you see electron inside of carbon. We're going inside the electron shell. Now we're going to see a nucleus, nucleus of a carbon atom, I guess, and inside the nucleus there are quarks. So we've gone all the way down to the size scale of 10 to the, I'll have to use my pen, 10 to the minus 16 meters. So it's really, really, really small. Sometimes called 100 attometers for people who like prefixes like atto, which is like never used. So here we see supposedly quarks, but we really don't know what quarks look like. So now we're down to the part of the universe that is essentially zero size so far as we can tell. There are lots of clues that quarks inside of protons and other things exist, but exactly what size they have, we don't know. Therefore, it's shown by all this nice, seemingly color scatter graph, but we don't know what this means. I think part of what they're trying to show is that it's hard to think of a quark as just a point and say it's a quark, because trying to pin down things in the quantum mechanical scale means that its momentum is uncertain, and then if its momentum is uncertain, if you try to look at it a second later, it's not where it was. And so sometimes the way to do that is just picture it as a cloud. It's around here. Try to find it, you can't really. The idea of things having zero momentum sitting still and being in one place is a concept of big things, macroscopic things like us. In the quantum world, it doesn't work very well. So we're going to increase the scale, and we're going to see another, supposedly these are protons, and inside, this is a carbon atom. Carbon atom is made of protons and neutrons. Protons and neutrons are nuclear things. Proton has a positive charge, and the neutron does not have any charge. So here's one of these things. Inside of this, quarks of different types are zipping around. The size scale is 10 to the minus 14 meters. So we'll zoom out again. And what you find is that most of the universe is empty space. So around this nucleus, there's just nothing. Nothing is there. the chance of finding a quark or a proton or neutron from this nucleus in this empty space out here is vanishingly small. It's just empty. Most of everything we'll find is empty space. It's hard to find stuff, even smaller. Finally, when we get to 10 to the minus 11 meters, we start to see chances of having an electron caught in your spherical ball of this size. On the time scale of a second or so. Chance of having an electron caught. Zooming out, we see, again, an electron ball. Electrons, again, themselves have no size that we can tell. Too small for us to measure. But the electron itself seems to be orbiting, but not in the sense of planets orbiting the sun, quantum mechanically jumping around a sphere. And so here that sphere is shown. That's the inner shell there, where the electron is jumping around. So here you see, well, that was part of a carbon atom, the electron shells of a carbon atom, and all these carbon atoms are all together, and they're making up a long nucleus of a much larger molecule that makes up DNA, which is, so here you see the double helix structure of DNA. So we've moved into biology at this point. Every living thing that we know of has DNA. That is essentially the code that the computer code that describes what it is and how to fix it. So if you didn't have DNA and you got a cut, it'd be hard to fix yourself. But your body knows how to do it, though. So, okay. So here are chromatin in the leaf of a nuclear cell. So we'll move out to the cell of a, so there's, as you saw going in, there's a leaf here, and here's the nucleus of that leaf cell. All kinds of biology going on there that's not important for this course is generally important. So here you see the cells of the leaf all together. At this point, at 10 to the minus 4 meters, we're in the realm, easily within the realm of the microscope, possibly within the magnifying glass. So those microscopes that you have at home in your closet, you could take those out, or when you go to biology or chemistry class, you might be able to see these things in a microscope. Probably someone on your hall, down the street in your house has something like that, and you can. It's kind of fun to look at. Just take stuff and look at it under the microscope. Let's clear that stuff and zoom out some more. And so now we're beginning to see the leaf. This is an oak leaf magnified 10 times. So now we're at 10 to the minus 2 meters, which is 0.01 meters. Zooming out. Now you actually see the leaf. This is 1/10 of a meter. Well, that was a centimeter before. So this is centimeter size. So this is 1/10 of a meter. So this is a meter. So when you're at the meter size, now you see many leaves in this tree. So keep going out, and here you see essentially the tree, but there's other trees around it. So we're at the size scale of a meter. So 10 to the 2 is 100 meters. So this box is now 100 meters. That's, what about a football field? So if you could punt a football or a soccer ball, you could possibly cross most of this distance. Here are buildings where humans supposedly work. I don't know what those buildings are. Here's a pond nearby. So now we're starting to see something that you might see in a zoom in on Google Earth. And it turns out this is the National High Magnetic Field Laboratory. And no, you wouldn't get extra credit if you were able to determine that just from this picture. It would be kind of strange that you were able to determine that, though. So we're now at a kilometer across, 1,000 meters. So zooming out more, we see that there's other things. There are roads now you can see. There are other buildings and houses within 10 kilometers. 10 kilometers is essentially the size of our city. But in Florida, it's not fully a city. It's part of a city, part of Tallahassee. Zooming out, you now begin to see a coastline. You can see it's actually, well, probably at this point you can't yet tell it's part of Florida. It's several counties in Florida that you're seeing, and it's 10 to the 5 meters, 100 kilometers. Okay, another factor of 10 out, 1 million meters. You're now seeing that that box is in Florida. People who recognize the U.S. now recognize this as part of the Florida coastline. Zooming out another factor of 10, you're beginning to take in the whole Earth. This is the western hemisphere of the Earth. This is South America here. This is North America here. This lecture is originating from just about here, I believe. Zooming out, we see the Earth as a blue marble, and now we see the orbit of the Moon. The Moon would be here. The Moon is smaller than the Earth. Just to be clear, you can't see the orbit of the Moon. It's just drawn in, so you can tell how large it is. Zooming out, you can't see the orbit of the Earth. It's not really blue. The Earth is blue, but the orbit is not. It's just drawn in just so you can see. I don't even know why they chose this width there. I don't know why. But the Earth can be seen, and you can see the orbit of the Earth, the orbit of the Moon inside that. Now you begin to see where other planets orbit. Here, this is Venus. This is Mars. Okay, how are we doing on time? All right. Here you see the inner planets of the solar system. The Sun finally is in view in the very center. The inner orbit of the two planets interior to the Earth are Mercury and Venus, as shown in white, and that should have been yellow, I guess. And no, green would be Venus, blue would be Earth, red would be Mars. So Mercury and Venus don't have moons, but the Earth has a moon. So the third rock from the Sun TV series, well, there's lots of smaller rocks. It was never really the third rock, but sometimes the moon is closer to the Earth than the Sun, so if you really want to be nitpicky, you might say that sometimes the Earth is the fourth rock from the Sun. Okay. Zooming out, you begin to see the outer solar system. So the red is Mars. This would be Jupiter, Saturn, Uranus, Neptune. Pluto may or may not be a planet, depending on the year. Pluto sometimes orbits inside the orbit of Neptune, but that is our solar system as we know it. Well, there's things further out, but they're not major planets. So our solar system begins to shrink at 10 to the 14th meters, 10 to the 15th meters, and eventually the brightest thing in our solar system is the Sun. Everything else just essentially shines by reflected sunlight. The Sun is clearly the brightest thing around, but the Sun is not a particularly bright star. So if you lived on a nearby star, you wouldn't think, hey, that Sun, it's really bright. Whose star is that? No, you just think, oh, there's another star in the sky. Not particularly different. Here you can see that it's even hard to see the Sun at this point. There are brighter stars around. Sirius would really get all the press. As you zoom out, you begin to see that the Sun is very hard to see, but part of many stars that make up the band of a galaxy, part of a spiral arm of a galaxy. So this is part of the spiral arm, and as we zoom out, we can see more of a spiral arm. During this class, you'll really begin to see, we'll show pictures of a better estimate of what the Milky Way, our Milky Way galaxy looks like. And as we zoom out more, this galaxy is this is our Milky Way. This one here is the Andromeda galaxy, sort of our twin neighbor. And we're at the furthest out that this is willing to go. So when that happens, you should be sure to click on the next tab and go even further out. So this is another zoom out that I will do, and this one gives a more accurate zoom out. So we'll start here. And here are the stars near the Sun. So here's the Sun. The closest star to the Sun is Alpha Centauri. Well, Alpha Centauri system. Of that system, the closest star is Proxima Centauri. One interesting note is that Alpha Centauri itself, Alpha Centauri A or B, I forget which one, is actually pretty similar to our Sun. It's a green-yellow star. It might have planets. So an interesting coincidence is one of the closest planetary systems to our Sun and the Earth is similar to ours and may have planets. We don't know yet. Other bright stars, Sirius, really bright, would light up the local neighborhood. The galactic center is in this direction, as it says. There's lots of other stars. Here we see the scale is 10 light years, so it takes light 10 years to go that distance. Okay, so let's zoom out. And we see other stars here. Now the galactic center is this way. Bright stars in the neighborhood are shown. So they're shown by their names. Bright stars are typically labeled by constellation names, and the brightest star in a constellation is usually called Alpha and the name of that constellation. So here we see, I bet I can't find one, Alpha Hydra. Ha, that's a bright one. Alpha Lin, and I forget what Lin stands for. Alpha Cassiopeia, brightest star in Cassiopeia. So there's lots of these stars here. Lots of bright stars light up the night sky. And now light takes 100 light years, 100 years to go from here to there. Zoom out again. So here we see our spiral arm, which is the Orion arm, essentially. There's other arms, Sagittarius arm. 1,000 light years is this thing, is that distance here. So we'll be seeing a lot of nebula this class. And some of these nebula, the Eagle Nebula is over here. The North American Nebula is over here. The Orion Nebula is over here. Rosetta Nebula is here. Crab Nebula is here. You'll see pictures of all of these. These are bright gas clouds that are not all that far from the sun. Just showing you about where they are, zooming out by a factor of 10 now. Here you see the Milky Way galaxy, which is a barred spiral galaxy. It has a bar in the center. This is not a bad guess as to what it looks like. You can see the Sagittarius dwarf, a smaller galaxy around ours. You can't yet see the other, although probably in the next one I'll hold off. There are globular clusters around the center of our galaxy, all around, maybe a couple hundred in total. The galaxy is very thin compared to its width. So this is 10,000 light years now. And we will zoom out again, this time by a factor of 10 again. Okay, here you see there are four galaxies you can see with your naked eye. You can see the band of our Milky Way, particularly from this area because we have nice dark skies here. Go away from the center of Houghton. If you go to so another galaxy you can see here is the Andromeda Galaxy, not yet shown. If you were to travel to the southern hemisphere, or far enough south, even Hawaii, you will see with your own eyes two other galaxies, the Large and Small Magellanic Clouds. They're kind of peculiar, well, particularly the Large Magellanic Cloud is kind of spiral in nature. The Milky Way has also lots of groupie galaxies that hang around because we're so cool. Actually, because we have lots of gravity. And some of these are mentioned here, the Ursa Minor dwarf, the Draco dwarf, Sagittarius dwarf we saw there, Sculptor dwarf. Lots of smaller galaxies, some of which, there used to be more, but we ate some. We're going to probably eat some more of these in the billions of years in the future because we're big and hungry, and that's what big galaxies do. That's partly why they light up in their spiral shapes. So we'll learn more about that. Zooming out again, we see this is 1 million light years from here to there. Andromeda, here's Andromeda. Yay, here's the Andromeda Galaxy right there. And its friends, its groupies, satellite galaxies they're officially called. So both together, all of this is called the local group of galaxies. And we'll review that too. So zooming out again, this time by a convenient factor of 20, we see, well, the Virgo cluster is here. So if we look in one direction, we can see a whole cluster of galaxies. There are other spiral galaxies not too different from our own. There are other kinds of galaxies. So our galaxy is not alone in the universe. There's lots of galaxies like ours. But even bigger than the Virgo cluster is the Virgo supercluster that has lots of other, well, groups around it. And also other clusters. So zooming out here, we see the neighboring superclusters. This is one, what does it say? Within 1 billion light years. So here we begin to see what's called large-scale structure of the universe. Other superclusters, there are great, well, at the beginning of being able to see great walls and voids. And you see structure on the universe. The universe isn't completely uniform, but it gets more uniform as you look at it at a larger and larger scale. So we'll look at that too. So here, as you see, when you get to the universe on the largest scales, so this is 1 billion light years here. This is essentially the visible universe up to, well, 13.7, essentially 14 billion, because we like to round things, light years. We see the universe suddenly becomes more uniform than before. Yes, it's spotty. Yes, it has filaments. But this is all fuzzed out, a big fuzzball in one sense. And that is our universe. So, going back to the lecture already in progress, he says trying to, oops, here we go, minimize that. Not being real successful. Here we go, in current slide. Okay, so we've just gone to these spectacular websites, which you can go to on your home computer, and you can play again. That Zoom in movie, you can play it until your friends complain. And eventually, the police will become involved. But you'd have to show it a lot for that. We've seen everything from quarks to the entire visible universe. Okay. So, now going through parts of the universe, let's talk about the Earth in very general terms. The Earth's atmosphere in particular. The Earth's atmosphere thins as you go up. So here we have the Earth's atmosphere as it goes up. So we live here below Mount Everest in the troposphere, where the air is nice and thick. As you go higher, the air becomes thinner and harder to breathe, which is why it's one of the reasons why it's hard to climb Mount Everest. The other reason is because it's easy to fall off. Up higher, there's weather balloons that float 50 kilometers or so. Up higher is the realm of where meteors burn up. Most meteors are little sand-sized grains that are floating around our solar system, orbiting the sun, and they intersect the Earth. Unfortunate for them, because they essentially burn up. They heat up and burn up. Above that, that's the mesosphere. And the realm of the thermosphere is the realm of aurora. So there are particles that originate from the sun, then get trapped by the Earth. Then when the sun undergoes some episode, it pushes on that part of the Earth, and these things fall into the Earth. But they're charged, so they fall down magnetic field lines. So they're usually seen in the north and the south. And when these high-energy particles, which are like protons and electrons, when they hit like things in the Earth's atmosphere, which is like oxygen and nitrogen, they cause the electrons around the nitrogen and oxygen to jump off, and then they come back. The electrons then come back, and when they come back, they emit light, and that's the light you see as aurora. Above that is when you go on the space shuttle, so you'll be able to look down on the aurora. And above that is essentially, well, the Earth's atmosphere thins out slowly. And eventually goes to essentially nothing, a higher vacuum than we can easily make on Earth. Here's one of the beautiful pictures. This was, I believe, taken from the space station that orbits up where the shuttle is, which we can see is about, well, it's a couple hundred meters high. It's a space shuttle, 400 kilometers high, about. So I prefer kilometers to miles. Kilometers are a standard unit. Miles are used here and in Great Britain. So I think the U.S. is, I guess, is expensive, but somewhat wimpy for not contributing to kilometers. But in the realm of astronomy, a kilometer is about a mile. It's less, so don't worry about it. So you can hear miles when I say kilometers. It's a little bit less. Don't worry about it. Next slide. So if you're on the space station looking down, you see really cool stuff. You see spectacular clouds. You can see land down there. You can see the Keweenaw Peninsula of Michigan. You can see the moon. Here's the moon. But here the moon is fuzzed out partly by the Earth's atmosphere. Here you can see blue because the Earth's atmosphere preferentially knocks blue light out from sunlight. And you can see a crescent moon, but the moon fades away because the Earth's atmosphere becomes more and more opaque as the more of it you go through. Okay, the different kinds of light. I think we reviewed last time Roy G. Biv, and we looked at the different kinds of light all the way from radio through microwave, through high-energy light like X-rays and gamma rays. Well, here we have low-energy light here. This is low energy, which means very red. And this is high-energy light here. And it's really difficult to read my writing, I'm sorry. But here's sea level down here. So here's where we're floating. And So here's the visible spectrum. This is where things don't make it. So this is where most light is absorbed, right on this boundary here. So the visible light makes it through. And that's why our eyes can see visible light. Because the beings who were born seeing infrared light, it was kind of dark down here. And then the lions and tigers would come and eat them, and they would say, gee, it's dark, and then something ate me. But we could see visible light, so we could see that. Similarly, people who had X-ray eyes, they'd say, oh, great, I can see X-rays. But then they get eaten by a tiger, and nobody cares. So visible light is good. Now, radio makes it down to the surface of the Earth, too. But it turns out that you're best off at the highest energy. You get the most photons at the highest energy. The sun emits most of its light in visible light. So if the sun was a radio emitter, which it is, if the sun emitted most of its energy in the radio, then there might be a reason why we might have radio eyes. But then radio eyes would be really big. So as you know, radio dishes are big. So we're best off in the visible. If we want to see things in the ultraviolet, in the X-rays, and the gamma rays, if we want to see things off the Earth, then we need to launch satellites that go up this high at least. And we have. In the past 50 years or so, we've launched satellites up to see all across the electromagnetic spectrum. And every time we see the sky, it's completely different. So we see a very unique sky in visible light. Okay, the nature of light. Light is electromagnetic radiation. It's essentially oscillating electric and magnetic fields. Yes, that's really weird. You don't have to know more detail than that, really. Colors we reviewed last time, Roy G. Biv, red, orange, yellow, blue, green, indigo, violet. Interesting story in indigo I won't go into. All light has energy. The more close you are to blue and violet, the more energy it has. So here we have energy of light in kilograms, meters per second squared. So the way to get units is do E equals mc squared, the famous E equals mc squared. So this is kilograms, this is meters squared per second squared. So it shows that I missed something. Kilograms, yes, should be squared. Another mistake. H is something called Planck's constant. It's really small. It tells how quantumly weird things are. And since it's so small, on our scales, it's not really quantumly weird. Or you have to know where to look to find it. Nu is frequency, and times things happen per second. So then we can calculate the energy just given its frequency. So white light that we see can be broken up by any number of devices. One is a prism into many colors. And so here we have a video image that shows white light coming in here, getting broken up into colors by a piece of glass triangle. This is normal glass you could find anywhere. And as it comes out, it's in colors. So most of you have seen a spectrum. Many of you have seen a prism. Many of you have seen glass that happens to do this. You can also do this with the right kind of reflecting media. But glass is the easiest way to do this. And this happens because light takes slightly different bending angles, different colors of light of different energies, and different speeds in glass and in whatever. Okay, so c is the speed of light. Lambda is the wavelength of light. So here's a quick problem. What is the energy of a red photon? Well, to do a red photon, you're going to use this expression right here. So E is equal to hc over lambda. So this is h. This is c. This is lambda in terms of meters. So you can look up lambda on Wikipedia, for instance, for a different color light, and it will just tell you. Just search for it on Google. So you plug these numbers in, being sure that you always use meters, not centimeters and meters. Here we have seconds, kilometers are good, and you end up with this energy of light is 3.06 and 10 to the minus 19 kilograms meters per second squared. Again, it should be meters squared, so I'll have to correct that. But the number's right. Okay, so radiation. How do you get radiation? How do you get light? We talk about this light. Where do you buy some? Well, we emit light. light is emitted by things you buy in stores. The sun emits lots of light, or light wouldn't be so popular. So we emit mostly infrared light because we're relatively colder than the sun. The hotter you are, the more energetic the light you give off. So everything that has a temperature, like when you're sick you have a temperature, well, even when you're not sick you have a temperature. So that temperature just is colder than usually when it is when you're sick. That temperature, the radiation you give off is called black body radiation. And it's black because we're not including reflected light. So if you were to take something and paint it completely black, which means it's not reflecting anything, even though it's painted black, it gives off all kinds of light. And that's black body radiation. So all incoming light is assumed absorbed. And the temperature that it gives off is the color that it gives off tells you the temperature it gives off, and that doesn't make any sense because you don't see anything glow like that. We don't seem to glow. But if you had infrared eyes, you could see us glow. So we'll come back to this one. So the question comes down to, is this useful? And it turns out that knowing about black body radiation is useful because you sometimes would like to know whether you should pick up something that's glowing red hot or blue hot. Would you rather pick up something red hot? So there's some fire going there, and there's two nails or something like that, or there's some kind of glowing pot that you want to take out, and there's two pots. There's a pot that's glowing so much it's red hot, and there's a pot glowing so much it's blue hot. Which one is hotter? And that's determined by, assuming these pots aren't reflecting, by the black body radiation. And the answer is that blue hot is hotter than red hot. So if we go back to the previous one, we can see that this is reddish, this is blue, red. This is blue in this direction, I believe. Yeah, as wavelength goes down. So here we see the intensity goes up. So as the thing becomes more blue, as you heat an object up, first it doesn't glow much at all. It's glowing in the infrared. You keep heating it up, it becomes red. You keep heating it up, it becomes blue. You keep heating it up even more, it becomes a little bit white, which is weird, but it's really so blue that the energy you can see and it's emitting almost equally among that, but it's more blue than anything, so it's sort of blue. And this is the temperature in kelvins. Okay. So a way to, in math, lambda max times T, the peak color that it gives off in terms of photons is called lambda max, wavelength, times the temperature is a constant. So temperature is measured in Kelvin. As again, lambda max is the brightest wavelength the black body emits. Remember, the sun is so hot it's not even red, it's green. We covered that last lecture. So the sun emits black body radiation. What you're seeing in the sun is not reflected light. What you see of the moon is reflected light. The moon is not that hot, but the sun is. Here you see something that's heated up for red hot. Sometimes when volcanoes are going off, if you see things that are really hot colors, it's time to go away because it's really hot. So not only that, it's time to go far away because it seems to be throwing off magna balls. This particular Mount Etna explosion in, I think, 2005. So the hotter something is, the more it glows. And that is determined by the Stefan-Boltzmann law. So in math, the energy it gives off is sigma, which is a constant, times the temperature to the fourth power. So E is energy, T is temperature again. Sigma is a constant called the Stefan-Boltzmann constant because this is the Stefan-Boltzmann law. And this law just says, as I said, hot stuff glows more. Stefan-Boltzmann law, hot stuff glows more. Heat it up, it's going to give out more energy, more photons. Here's another beautiful picture, an eruption in Iceland where you see both very hot stuff and you see, actually, this isn't actually green hot. You see aurora at the top. This is glowing from black body radiation. This is not. So there can be other types of radiation emitted. So here's an example. Let's say you have two stars and they're the same size. One is red hot and the other is blue hot. Which star emits more energy? And the answer to that, it's the blue hot star. And now we come into actual numbers. Well, really? Okay, well, how much more? Well, if it's one is red hot, one is blue hot, let's assume that the temperature of one, the blue hot one, is twice the temperature of the red hot one. If that's true, then the ratio of the blue hot one energies emitted to the ratio of the red hot one's energy emitted is sigma T blue to the fourth divided by sigma T red to the fourth. But the sigmas cancel because they're both in the numerator and the denominator. And the temperatures, we know that one of them is twice the other one, so this works out to T to the fourth, 2 to the fourth. And we know that 2 to the fourth is 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. And so we actually know the answer to this one. If one is twice the temperature of the other and they're the same size, then one gives off 16 times more energy. You might think of it as cooling 16 times faster. So let's become even more sophisticated. Black body luminosity law. So in the Wikipedia page for the black body and other laws, they have P, SEMT. I prefer L for luminosity. So how bright is an object? The energy per second that it gives off is 4 pi, which tells you that it's giving off in all directions, its radius squared, and then we have, back to the Stefan-Boltzmann law, the sigma, which is a constant, times its temperature to the fourth. So this looks like a lot of mumbo-jumbo at first, but it tells you something very directly. It says two things, one of which you already know. The hotter it is, the brighter it is, the more it glows. And this other thing says, oh, also, the bigger it is, the brighter it is. And these two things work together. Pi is the same number that we all know, at least mostly several digits. So in other words, trying to move into words here, the black body luminosity law is bigger and hotter stuff glows more. Now, why is this different from the other one, that hotter stuff glows more? Because last time we assumed everything was the same size. So now we got more sophisticated. We say, oh, what about big stuff and small stuff? Let's throw that in too. And so this is as sophisticated as we're going to get. Luminosity is 4 pi r squared sigma t to the fourth. This is one of the mathier lectures, by the way, we're going to have. Usually we're not going to be this mathy. Okay, so here we see a open cluster of stars. Now, we're not covering open clusters right now, but it sure looks cool. An open cluster is good because all the stars are approximately at the same distance. And if they're the same distance, then they're apparent. How bright they appear to be isn't dependent on how far they are, because they're all just about as far away. And here you can see, well, it's called a jewel box. There's stars that glow mostly in the blue, stars that glow mostly in the yellow. You know, bright stars, they're dimmer stars that glow mostly in the yellow. You know, dimmer stars that glow in the blue. And so we'll be able to learn things about the radius and temperature of these stars from how bright they are and from the colors they are. So here we can say this star here is really bright and it's really blue. So it's big and hot. Here we see a star that's even brighter than the other one, and it's red. It's more red. And so we can say, well, it's not hot, but so it must be really big to give off to be that bright compared to the other stars. So this star here, really big. So this black body idea and the Stefan-Boltzmann law tells us things about stars now. Just from looking at stars, we can tell that some are bigger and brighter than others. Okay, so let's do another example. So let's say two stars have exactly the same color, and that one star is twice the radius of the other. Which star has the higher luminosity? Well, the answer to this would be the bigger star, because once this gets put in, it's a bigger number. Everything else is the same. This becomes bigger. So now comes the mathy question, how much more? Again, I like to work in terms of ratios, so you don't have to look up constants like this. So you won't have to look up constants like this in the course. It's just for explanatory purposes. So how much more is the star that's twice the radius and the other star that has the same color? How much brighter is it, assuming they're at the same distance? So you take the ratio, L big to L small, so you put 4 pi r big squared sigma t big to the fourth divided by the other one, 4 pi, this is all in parentheses, 4 pi r small squared sigma t to the fourth. So the pi's, they're divided by each other and they go away. The sigmas, they're divided by each other, they go away. 4's gone. Left with the t's, Now, we said they're the same color, and since we're assuming a lot of things, that means they're the same temperature. So the T's also fall away. So the only thing left is the radius. So here you have then the ratio of the luminosities, the brightnesses, is the ratio of the radiuses, radii squared. And again, we said that one is twice the size. So that twice gets put in there. And now we can tell that the star that's twice the radius of the other has 4 times the luminosity, 4 times the brightness. All from this formula. So just study the formula, and you don't have to understand really the numbers of the concepts, just the concepts of the formula. And from reading the Wikipedia pages, hopefully that will become more clear, and watching this lecture maybe around 6 times. So here we come back to the first slide of the lecture, and this tells us 2 things. First of all, we'll be ending a little bit early today. Second of all, I now describe what this is. This is a famous star system, which you can see with binoculars. Even you can see the star system without binoculars, but it's cool to see with binoculars in a small telescope. It's called Albireo, and it's a double star. So when you look there, it looks like one star to the unaided eye, but when you use good binoculars or a small telescope, or even a big telescope, it gets broken up into more than one star. There's 2 stars there, and these stars probably are orbiting each other. But they orbit each other with such a long time period, we really haven't been able to see that yet. But these stars are approximately the same distance. And there's a yellow star, and there's a blue star, so now we know something about these 2 stars. We know that since the yellow star is brighter than the blue star is hotter than the yellow star because it's bluer, and the yellow star is bigger than the blue star because it's brighter. And with that, I will conclude today's lecture. Next time we will have another lecture and review the astronomy pictures of the day. So until next time, I'll see you. Bye-bye.